Welcome to Narada Academy. In this video, we are going to discuss about countable and uncountable sets in the set of real numbers. Okay, see first let's start with the definition of a finite set. You all know what's a finite set. Okay, that is finite set means the set ends at certain point, isn't it? See 1, 2, etc. up to n. This is a finite set. So mathematically, how do you define a finite set? So a set S is said to be finite if there exists a bijection, that is one-to-one correspondence from the set 1 to etc. up to n onto the set S. Okay, so if you want to prove this S is a finite set, for that what you have to do? You have to take this set 1 to etc. up to n, that is the natural number starting from n to n, starting from 1 to n, and you have to get a bijection from this set onto this S. Then if the bijection exists, okay, the set is said to be finite. Otherwise, the set is said to be infinite. So this is the mathematical way of defining a finite set. But by looking at the set itself, you can say whether it is finite or infinite. So there no need to be any proof for this one. Okay, next one. So if the set is finite, it's okay. If the set is infinite, two cases arise. So one is enumerable. The another one will become what? Not enumerable set. So enumerable means what? That means if you have a set and the elements of the set can be arranged in some order. Okay, this is the first element, this is the second element. If you can arrange the elements in some order, that set is said to be what? Enumerable set. So yeah, mathematically, how do we prove the enumerability of a set? So we develop a one-to-one correspondence from the set of natural numbers onto the set S. See, how do you prove the finite set? How do you prove a set is finite? We establish a one-to-one correspondence from 1 to n onto the respective set S. In the same way, if you want to prove a given set is enumerable, that is the given set can be arranged as first element, second element and so on, etc. So for that what you have to establish? The same thing. Okay, you have to establish a one-to-one correspondence. Here you have taken finite set. Now here you have to take what? Natural numbers. Natural numbers to the set S, you have to establish a one-to-one correspondence. Because natural numbers is the set used for counting, no? For counting purpose or arranging purpose, no? So from natural numbers, you have to establish a one-to-one correspondence to the required set. So if there exists a one-to-one correspondence, the set is said to be enumerable. Enumerable is nothing but we can arrange the elements in this is the first element, second element in that way, or we can count the elements like this 1, 2, 3, 4. We can count. So if such kind of countability is there, that is said to be what? Enumerable set. Okay. Now let's come to the main definition. A set is said to be either countable if it is either finite or enumerable. So if a set is finite or enumerable, it is said to be what? Countable set. So the set may be finite or infinite. What you have to do? It can be countable or uncountable. Uncountable means you cannot arrange the elements in some order. Element 1, element 2, in that order you cannot arrange for uncountable sets. Okay, now let's see some examples. Now consider the natural numbers. The natural numbers is obviously enumerable set, because for proving enumerability, what you have to do? From natural numbers to the required set, you have to establish a one-to-one correspondence, no? So the set itself is n here. So by identity mapping, f of x is equal to x, you can prove bijection. Okay, therefore n is enumerable. Since it is enumerable, it is countable. Next, consider the z set of all integers. Integers is also countable. How it is countable? See, what are the elements of the set of integers? All the negative numbers, that is minus 1, minus 2, minus 3 and so on, and the positive 1, 2, 3 etc. and 0. So this is the set of all integers. I have to prove this is enumerable. Okay, so for proving it is enumerable, I have to establish a one-to-one correspondence from n to, that is the natural numbers, to z. So for that I am defining one map like this. Let f of n equal to 1 by 2 into n minus 1 for n equal to 1, 3, 5. That is for odd values of n. This is the definition. For even values of n, the definition is minus n by 2. Okay, this will give you a one-to-one correspondence. Okay, right? So how to prove one-to-one correspondence? Suppose if n1 and n2 belong to n. So first I am taking it for odd integers. Okay, n1 and n2 are odd integers which belong to n. Suppose if f of n1 equal to f of n2, then what happens? 1 by 2, by definition 1 by 2 n1 minus 1 equal to 1 by 2 n2 minus 1, no? So n1 minus 1 equal to n2 minus 1, that implies what? n1 equal to n2. Therefore this is what? A bijection when both are what? When both are odd positive integers. Suppose when they are even positive integers, the same kind of proof applies here. When n1 and n2 are even, then what will you have? Minus half n1 equal to minus half n2, that implies n1 equal to n2. If one odd, the another one even means both cannot be equal to each other. So one is odd, one is even means what? Both the numbers are different, therefore the images will obviously become different. So what we have proved in this one, distinct points have distinct images. That means the function is a bijection. Therefore there is a one-to-one correspondence from the set of natural numbers onto the set of integers. So Z is enumerable. So enumerable means what? Countable. This is the theoretical proof. Okay, the outline of the proof is given here, but you can verify it directly. See, here I have written the elements of n, here I have written the elements of z. See, when n is equal to 1, substitute here. What will be the image? 1 minus 1 is 0. 0 will be the image. When n equal to 2, the image is what? Minus 2 by 2 is minus 1. When n equal to 3, the image will be what? Plus 1. For 4, it is minus 2. 5, it is plus 2. So you can see the numbers are alternately positive and negative coming. So no repetition is here. That means each element in the domain has a distinct image and each element in the range has a distinct pre-image. Therefore this is a bijection. Okay, therefore Z is also a countable set. Okay, next one, let's see one theorem. Every subset of a countable set is countable. Okay, suppose A is a countable set, right? Let B be a subset of A. Then two cases arise. Either B can be finite or B can be infinite. If B is finite, obviously it will become countable. Suppose B is infinite, then what to do? Okay, since now we have assumed A is countable, no? That means what? The elements of A can be arranged in certain order, A1, A2, A3, etc. Isn't it? So I have written the elements of A in some arrangement. Now B is a subset of A only, no? Therefore elements of B will be also of the form AI. Okay, first what I am going to do is I am trying to arrange the elements of B in some order. For that I am going to choose the index of this, that is the index is there, no? I am going to choose n1 as the smallest index for which A n1 belongs to B. Okay, here infinite number of elements are there. All these elements are not in B. Only few elements of this are in B. So among the few elements I am choosing the smallest index first, A, and I name it as A n1 and I put it in the first place. Okay, and then in the remaining set, from A I have removed one element, no? From the remaining set I choose the next smallest index which also belong to B. That element I am going to write it in the second place. So etc. Simply the concept is, when B is an infinite element, look at the index of elements of B and arrange it in some order and name the elements as A n1, A n2, A n3, etc. Why do you write it like this? What is the purpose? What we have to do? We have to prove it's enumerable, no? For proving enumerability, we have to establish a one-to-one correspondence from the set of natural numbers to B, isn't it? So for that I have to define a function. For define a function, I need some kind of format here. For that format only I am doing like this. Nothing I have done here. Understand? That is, I am arranging the elements of B such that the index, that is the suffix A, n1, A, n2, these are in ascending order. n1, n2, n3 are in what? Ascending order. The numbers need not be continuous here, but I am renaming them A, n1, A, n2, A, n3, etc. With this rearrangement, you define a mapping f from n to B as f of k equal to A n k. Then this will be a bijection. Surely it's a bijection, no? Therefore, what we say? B is countable. So the conclusion is, every subset of a countable set is countable. Okay. As a corollary for this theorem, every superset of an uncountable set is uncountable. Okay. That is, if B is an uncountable subset of A. Okay. B is an uncountable subset of A, then A must be uncountable. So for that, see, B is a subset and B is uncountable. Suppose A countable, if A is countable, from the previous theorem what can you say? Every subset of A is countable, no? But B is uncountable here. Therefore it is not possible. Therefore what? If a subset is uncountable, then the superset also uncountable. This is a simple logic only, you can understand. Next theorem is countable union of countable sets is countable. So what do you mean by countable union? Union we know, isn't it? Union means we write all the elements of the sets together. What do you mean by countable union? Again the same thing. See, this is union n equal to 1 to infinity an I have written, no? That is a1, a2, a3 etc. are countable sets. Then a equal to union n equal to 1 to infinity an. This is called countable union. That means a1, a2, a3 etc. That is this n runs from 1 to infinity. That means n is countable, no? So this is called what? Countable union of countable sets is countable. Okay. The another one type of union is there, that is called arbitrary union. In arbitrary union, you will be writing it as something like, see, union varies over alpha, a alpha. Okay, this alpha may be any real number. Okay, this is called what? Arbitrary union. Okay, this is not countable union. This is called what? Arbitrary union. This need not be countable. Okay, this is not possible to prove countability. But what we prove here, countable union of countable sets is countable. So first I am assuming a1, a2 etc. are all countable sets. That means what? I can write the elements of a1, a2 in some order. I can arrange the elements of these sets in order. So I am writing the elements of a1 as a11, a12, a13 etc. a2 as a22, a21, a22, a23 etc. In that way I have written the elements of all the sets. Okay. Now I am going to take the union. So the union will contain all these elements. Now I have to prove that union is countable. For that, what I have to do? Just I have to arrange the union in some way. Here some kind of arrangement is there, no? In that way, the union should also be arranged in some possible way. So for that, what I am going to do is, I am going to define height of the element. If Iij is an arbitrary element, define the height of the element as I plus j. The suffix is there, no? The index. You add the numbers I plus j. This is defined as height. So this element is of height 2. And this is of height 3, and this is also of height 3. Two elements of height 3, and this is of height 4, and this is also of height 4, and one more element a 3 1 is also height 4, and so on. So you see there is one element of height 2, two elements of height 3, three elements of height 4, and so on. In general, m minus 1 elements are of height m. So I have obtained one arrangement. How? I am going to arrange the elements according to their height. So first element of height 2, next two elements of height 3, next three elements of height 4, next four elements of height 5, five elements of height 6 etc. So some arrangement we have obtained, no? Therefore the set union n equal to 1 to infinity an is countable. That is countable union of countable sets is countable. Okay, right. Next theorem, the set n cross n is countable. So n cross n, that means natural number comma natural number, two tuples, isn't it? So let me define an equal to, okay, set of all ordered pairs of the form n comma 1, n comma 2, n comma 3 etc. If this is n here, n with 1 2 3 4. Okay, right. This set is obviously countable, isn't it? Because if you define a mapping f from n to an as f of k equal to n comma k, then this will be a bijection. Therefore this set an will be countable. So if an is countable, what about arbitrary union? That is n equal to, arbitrary union, no, countable union. What is countable union of an? N equal to 1 to infinity an. This will become equal to n cross n. That is, you change n. If it is a1, it will be what? 1 1 1 2 1 3 etc. If it is a2, it is 2 1 2 2 2 3 etc. If it is a3, 3 1 3 2 etc. So if you take countable union of all these an, that will give you the set n cross n. Since each an is countable, their countable union is also countable. Therefore n cross n is countable. Okay, the next one is the set of all positive rational numbers is countable. So how to prove the set of all positive rational numbers is countable? Let me define one set A, capital A equal to set of all ordered pairs PQ, where this PQ belong to n cross n and PQ are relatively prime numbers. Okay, PQ are what? Relatively prime numbers. Obviously, this is a subset of n cross n. Since n cross n is countable, A is also countable. Okay, now let's come to the question. Positive rational numbers. Positive rational numbers. Let Q plus denote the set of all positive rational numbers. How do you define positive rational numbers? They are in the form P by Q, where P and Q are non-zero numbers, isn't it? That is natural numbers, and they are relatively prime numbers. So you can establish a one-to-one correspondence between this q plus and a, as f be mapping from a to q plus defined as f of p comma q equal to p by q. Obviously this will be a bijection. Therefore, since a is countable, q plus is also countable. So what do we conclude? Q plus is countable. That is, the set of all positive rational numbers is countable. Next one, from this we can conclude the set of all negative rational numbers is also countable. This is just obtained by developing a bijection from positive rational numbers to negative rational numbers, as f of x is equal to minus x. Okay. So negative rational numbers is also countable. So from all these results, I am concluding the set of all rational numbers is countable. This is an important property. The set of all rational numbers is countable. How it's countable? Rational numbers is nothing but set of union of positive rationals, negative rationals with 0, isn't it? Each one is what? Countable here. Therefore, their union is also countable. Therefore, Q is countable. Next one, the set of all rational numbers in the closed interval 0 to 1 is countable. See, rational numbers itself is countable. So, every subset of it is also countable. Therefore, the set of all rational numbers in this closed interval is also countable. Next one is the set 0, 1 is uncountable. So, here I am taking all the numbers from 0 to 1. In the previous example, I have taken only the rational numbers. Here I am taking all the numbers between 0 and 1. So this is uncountable. Suppose if it is countable, we are going to prove this theorem by contradiction. Suppose if this is countable, then there exists a bijection f from n on to 0, 1, isn't it? That means what? Every element of 0, 1 can be arranged in some order as image of 1 plus image of 1, image of 2, image of 3, etc. So all these numbers are between 0 and 1, no? So they will be of the form decimal form, 0 point something. So let me write f of 1 equal to 0.a11, a12, a13, etc. f of 2 equal to 0.a21, etc. So these are all decimal numbers which are lying between 0 and 1. Now let me define a new decimal number with bn. I am going to take bn equal to 1 if ann is not equal to 1 and bn equal to 2 if ann is equal to 1. Then if a11 equal to 1, b1 will be 2. a11 is not equal to 1, b1 equal to 1. Let me define one number y equal to 0.b1, b2, b3, etc. Here definitely this number is a decimal number, so it belongs to 0, 1. But it differs from f of 1 in the first decimal place. It differs from f of 2 in the second decimal place, etc. It differs from f of n in the nth decimal place. Therefore, this is an element of 0, 1, but it doesn't belong to the image set f of 1, f of 2. That means f is not a bijection. Therefore, this establishes a contradiction. Hence, we prove 0, 1 is uncountable. So, since this small interval is uncountable, its superset, the set of all real numbers, is uncountable. Next one is the set of all irrational numbers is uncountable. Suppose if irrational is countable, in that case what happened? Rational union irrational is our real numbers, no? Rationals is countable, that we know. R is uncountable, that also we know. If irrational is countable, this will establish a contradiction. Therefore, irrational must be what? Uncountable. Next one, let Pn be the set of polynomial functions of degree n defined by relations of the form f of x, that is nth degree polynomial with the non-negative integer coefficients. We have to prove it is countable. Okay. Now we are going to prove this by induction on n, degree of the polynomial. See, for n equal to 0, 0 degree polynomial means what? That is set of all a naught, integer coefficients only, no? So, non-zero polynomial means a naught belong to z minus 0. So, this we know the set z is countable, therefore p naught is also countable. So, set of polynomials of 0 degree is countable. Let me assume that set of polynomials of degree k is countable for some fixed k. I am going to prove it for k plus 1. For proving countability for p k plus 1, I am going to define one set sm and s minus m. Sm is nothing but I am going to take one polynomial of kth degree. I am going to add k plus 1th factor with coefficient m x power k plus 1. The same thing with negative sign, I am going to take it as s minus m. Obviously, these two will be countable because we are taking only what? Kth degree polynomial, no? With that one, I am adding only one single member. Therefore, both of them will be countable. If both of them are countable, their union is also countable. Okay, so their union is Tm. Tm equal to Sm union S minus M is also countable. What is this Tm? Tm is the collection of all kth degree polynomial along with the term k plus 1. Therefore, their union m equal to 1 Tm, that will give you different coefficients for k plus 1th term, no? So that will give you the set of all polynomials of degree k plus 1. This is also countable. So assuming pk is countable, I derive the result pk plus 1 is countable. Therefore, by induction hypothesis, pn is countable. Okay, so what is pn? Set of all polynomials of degree n. Right? Next one is the set of all polynomials with integer coefficients is countable. So in the previous case, we have proved that what? That is polynomials of degree n only. Here, polynomial functions with integer coefficients means the degree may be anything. That is, in the previous case, we proved only for nth degree polynomial. This is for any value of n. So, p equal to union n equal to arbitrary union of, sorry, not arbitrary, countable union of n equal to 0 to infinity pn. So, countable union of pn. Since each pn is countable, p is also countable. Next one, algebraic and transcendental number. Algebraic number means if you have a polynomial with rational coefficients, the roots of the polynomial are called algebraic. So otherwise, a number is said to be algebraic if it is the root of some polynomial equation with rational coefficients. If any number is not algebraic, that number is said to be transcendental number. See, real numbers can be classified into two parts, no? Either it may be a rational number or an irrational number. This is another classification. One is either algebraic or transcendental. Okay, so the first one is the set of algebraic numbers is countable. Okay, so let us denote Qn as the set of all polynomial functions of nth degree. Then Qn is countable. Okay, let Qn is countable means all the polynomials of Qn can be written in the form fn1, fn2, fn3, etc. No? Now, each polynomial will be having at most n roots. You take any arbitrary f and k and let the roots of this polynomial be represented by the set a n k. Then a n k is countable because it can have at most n elements. Then a n equal to countable union of k equal to 1 to infinity a n k is also countable. This a n will give you the set of all roots of, collection of all roots of this Qn. Okay, then you take a equal to union n equal to 1 to infinity an. This will also be countable because this is also countable union, no? But what is this a? This a is nothing but the collection of all algebraic numbers. So we have proved algebraic numbers are countable. So from this we conclude transcendental numbers are uncountable because already I told you, no, real numbers are classified into union of, one is rational with irrational, another combination is what? Algebraic with transcendental. If set of all algebraic numbers is countable, then transcendental must be uncountable. Next one. Next, let's see some examples and properties of transcendental numbers. See, all transcendental numbers are irrational numbers only. But converse is not true. That is, all irrational numbers are, not all irrational numbers are transcendental. Example, you see, square root of 2 is an irrational number, but it is not transcendental because root 2 is the root of the equation x square minus 2 equal to 0, no? So this is an equation with rational coefficients and root 2 is the solution for this. Therefore, root 2 is an irrational number, but it is not transcendental. So all transcendental are irrational numbers, but not all irrational numbers are transcendental. This is an important property. Let's see some example for transcendental numbers. E power a is transcendental when a is algebraic. That is e power 1, e power 2, e power 3, etc. for non-zero a value. Next one, pi is transcendental. E power pi is transcendental. Okay, right. Next one is, see, a power b. A power b with a is algebraic but not equal to 0 and 1, and b is an irrational algebraic, 2 root 2. This is an what? Transcendental number. This is base is a and the power is b. This base must be an algebraic number and the power must be an what? Irrational number. In that case, a power b is an transcendental number. The next one is sin a, cos a, tan a, secant and cot a. All are transcendental when a is a non-zero algebraic number. Only when a is algebraic, these are transcendental. See, sin pi by 2. This pi by 2 is not is not an algebraic number. No, this is a transcendental number. Therefore sin pi by 2 is algebraic. Sin pi by 2 is equal to what? 1 only. No, it is algebraic. Why it is not transcendental? Because this is transcendental, therefore sin pi by 2 is not transcendental. So look at the definition, look at the property correctly. Sin A is transcendental only when A is non-zero algebraic number. So here A is not algebraic, therefore these are not transcendental. Next one is log A with base B is transcendental when A and B are positive integers, not both of same powers. That is, both of them are not like 2 power 2, 2 power 3, not like that. Okay, in that case, what, this is also transcendental, and here A should not be equal to 1. Okay, that's all. Thank you.